Hi everyone and welcome to this webinar. Do you want to know what Wi-Fi will be like in 2025? Well, today I'll tell you all about the next generation standard IEEE 802.11be, that is Wi-Fi 7. I'm Gio, an assistant professor at UPF in Barcelona and a wireless communication expert. I've been lucky to collaborate with Wi-Fi experts, and here I'd like to acknowledge the great contributions of my colleagues Adrian, Lorenzo, David, and Boris. So the good thing about answering that question, what will Wi-Fi be like in 2025, is that it entails learning about several intertwined topics. So here's an outline of them. We'll learn a bit about the history of Wi-Fi and how it has evolved to present day 11AX or Wi-Fi 6. We'll understand what motivates a further evolution towards 11BE or Wi-Fi 7. We'll review in detail the new features in next generation Wi-Fi from a technical standpoint. We'll review a total of 8 features, and some of them can be seen as direct upgrades over 11AX, while others are truly disruptive new ideas. Finally, we'll go through some new performance evaluation results to appreciate the potential improvements brought by such new features. So let's get started. So who doesn't use Wi-Fi? Well, after 1 year of lockdown, we can hardly overstate the importance of Wi-Fi for businesses, entertainment, and social relations. Wi-Fi has some clear advantages compared to other wireless technologies. First of all, the use of spectrum is free, which means it comes without having to buy a license. Second, Wi-Fi devices are widely diffused with 13 billion of installed devices. Wi-Fi is the king technology indoor for residential, public, enterprise, and industrial deployments. Wi-Fi is expected to generate a global value of $3.5 trillion by 2023. However, these advantages bring along some challenges as new digital applications are adding more and more stringent requirements in terms of capacity, delay, and reliability. So increasing capacity in Wi-Fi is somewhat a traditional problem, whereas targeting low latency and high reliability is a paradigm shift. So before telling you about 2025 and beyond, let's have a look at how Wi-Fi got here first. So in 1997, the original 802.11 standard was defined with carrier sense multiple access and collision avoidance. Then in 99, 11B was defined to extend throughput up to 11 megabits per second, and both standards were working in the 2.54 gigahertz band. Then 11A was defined for operating in the 5 gigahertz band, and when the FCC allowed the use of OFDM in 2.4 gigahertz, then 11G was created for that. More recently, in 11N, the key to enhance throughput was spatial multiplexing. Channels also had a larger bandwidth, 40 megahertz, formed by using two contiguous 20 megahertz channels. Moreover, 11N allowed up to 4 spatial streams to be multiplexed, but towards a single user only, so no multi-user MIMO yet. Then in 11AC, larger bandwidths were introduced, 80 and 160 megahertz, and the use of channel bonding, as well as support for downlink multi-user MIMO up to 4 users. Then 11AX provides an increased average throughput per user in high density scenarios such as train stations, airports, stadiums, etc. And among the new features in 11AX, we can highlight the introduction of both uplink as well as downlink multi-user MIMO with up to 8 users. The next standard being developed has a name, it's 11BE, and this standard will be almost surely certified as Wi-Fi 7. The technical name for 11BE is actually extremely high throughput, but despite the name, this amendment will be much more than high peak data rates. So surely 11BE is projected to support at least 30 gigabits per second per access point, which is about 4 times as fast as Wi-Fi 6. But the 11BE task group also recognized the need for lower latency and higher reliability to enable time-sensitive networking use cases. And last but not least, backward compatibility and fair coexistence with previous 802.11 devices were also listed among the objectives. So regarding the timeline, in 2018, the extremely high throughput topic interest group and then the study group were formed. And these initial activities contributed to the creation of the project authorization request, followed by the formation of the 11B task group in May 2019, right? So the task group is currently focusing on the writing of the first draft, and the certification of the first 11B products is expected in the first half of 2024. To speed up the development of 11B, the standard group agreed to first place the spotlight on a set of high priority features, which are due in 2021, postponing the remaining features. So the main criteria being considered to prioritize features are their gain complexity ratio, their time to standardize and to implement, the associated interest and market needs, of course. And this timeline and list and subdivision into releases is evolving, right? So some of these features are direct upgrades over 11AX, whereas other features are more disruptive changes. So for the sake of clarity in this talk, I divided the 11B targeted features into two categories. The first category includes key upgrades over 11AX regarding the bandwidth, resource unit allocation, spatial multiplexing, modulation coding schemes. And the second category includes disruptive improvements associated to retransmissions, multi-link operations, and multi-access point coordination. Right, so in what follows, I'll guide you through each and every one of them. So let's get started by looking at the main upgrades from 11AX. The first feature I'm going to describe is the allocation of up to 320 MHz bandwidth per access point. This along with a more efficient utilization of non-contiguous spectrum. So for over 20 years, Wi-Fi has been working over two bands, 2.4 and 5 GHz. But recently, in April 2020, the Federal Communications Commission in the US cleared the way for a third band, which is the 6 GHz band. And other countries worldwide are following up. For example, I am aware of South Korea and the UK. So this 1.2 gigahertz of spectrum that will be available in the 6 gigahertz band is basically more than double than what we currently have available in the 5 gigahertz band. And remarkably, since only Wi-Fi 6E and Wi-Fi 7 devices will be able to operate in this new band, they will have, at least at the beginning, a pristine low interference setting. So this new spectrum obviously opens up new possibilities, such as using extremely wide channels, and this is called channel bonding. So let's learn a little bit more about it. So channel bonding allows to use multiple channels to achieve higher transmission rates and therefore higher throughput and lower delay, etc. Right? So in 11AX, access points and stations can adaptively select the bandwidth for each transmitted frame. And there's a defined set of embedded channels with primary channels and secondary channels, right? So having accessed the medium in a primary 20 MHz sub-channel, a device can expand the bandwidth through some iterative concatenation of secondary channels if they're idle. Okay, so in other words, if the secondary 20 MHz is idle, then the station can transmit in a 20 MHz channel. And then if both the secondary 20 MHz and the secondary 40 MHz channels are idle, then 80 MHz is available, right? So this is great. However, in real dense deployments with many basic service sets, so basically many access points operating in the same area, 80 MHz and 160 MHz channels may not be easy to find. So what to do in that case? So in cases of high channel occupancy, channel bonding will suffer, partially because the spectrum is fragmented, and this is because there are many legacy Wi-Fi networks that use, for example, only 20 megahertz channels, right? So for instance, consider some 11AX network that is able to transmit over 80 megahertz, okay, but the secondary 20 megahertz channel is almost always busy. So this prevents the 11AX network to use the 40 megahertz secondary channel, even if the 40 megahertz is idle all the time. So to avoid this in 11AX, preamble puncturing was introduced, and preamble puncturing allows an access point to transmit in punctured 80 or 160 megahertz channel when part of the secondary channels are busy, right? So this is designed to enhance channel utilization for dense access point deployments where 80 or 160 megahertz may not be fully available, right? So note that to implement this preamble puncturing solution, 11AX relies on OFDMA because non-contiguous channels can only be allocated to different stations. So we will come back to this later. So as you can see from this example, assuming an 11AX access point with full buffer for two stations, station A and station B, the performance gains of preamble puncturing are clear. So most of the transmissions that use default channel bonding on top of the slide only allow access point to use 20 megahertz channel, right? Because the secondary 20 megahertz is busy in gray. However, if you use preamble puncturing, which is the plot in the middle of the slide, the secondary 40 megahertz channel can always be used even if the secondary 20 megahertz is busy. So, and since Wi-Fi 7 devices will be able to operate in the 6 GHz band from the beginning, the plan is to increase the maximum channel bonding from 160 to 320 MHz. Okay, there are also discussions about defining new channel access rules, for example, removing what's called EDCA, so allowing instead access points to control all the transmissions, both in uplink and downlink. This is to achieve a more efficient use of the resources. Currently, this cannot be done in the lower bands because there are many coexistent devices and technologies that they still need to be compatible with, right? So, but this will be feasible in the clean 6 GHz band once it will be open. So coexistence with current technologies needs to be managed. These include like fixed and satellite systems, also potentially 5G new radio license. And in the 6 GHz band, Wi-Fi may not be treated as an incumbent as it was in the 5 GHz band. I'm now going to focus on another very interesting feature of 11BE, which is the possibility to allocate multiple resource units to the same station. Let's see what this is about. So first, let's recall how OFDMA works in 11AX. So the idea behind OFDMA is as simple as that multiple devices can be simultaneously scheduled in groups of different subcarriers, okay? So those groups of subcarriers are called resource units or RUs, okay? This might reduce the channel access delay, and it also adds some extra flexibility to distribute resources between devices that have different traffic profiles. So in the first case, in the example on this slide, you see the two stations transmit sequentially, so without OFDMA, whereas in the second case at the bottom, there's a single but larger OFDMA transmission from both stations. This is triggered by the access point, to which the access point responds with a block acknowledgement. Okay, so this second OFDMA approach clearly has a shorter total transmission time, therefore it's more efficient. So in the previous example, each station was assigned certain resource units or certain frequency tones, okay? And here, the top right of this slide, you can see the possible ways of assigning such resource units. So an 80 megahertz channel corresponds to 996 resource units, 40 megahertz corresponds to 484, and so on, okay? The smallest division is 26 tones. So different sizes of resource units are very useful to accommodate for different traffic needs. And in 11AX, the access point can take the role of a scheduler, so it can decide when to initiate transmission, both in uplink and downlink, and it can allocate the corresponding resource units to the stations. Okay, so for that, obviously, the access point requires channel and buffer information from the stations. Okay, so in the example we see at the bottom of this slide, the access point reserves the channel by using the multi-user RTS CTS mechanism. Okay. Then it transmits a trigger frame to allocate resource units to 3 stations for uplink transmissions. And we see the station 1 in lighter blue gets the largest resource units because it has more packets in its buffer, in this case 4 packets, okay? And after transmission, the access point replies with a multi-station block acknowledgement, okay? So all of this is great, but there is indeed room for improvement because in fact, we didn't use the whole 80 megahertz channel in this example. So notice that station 1 got 40 megahertz, station 2 got 20, and station 3 got half of a 20 megahertz channel. So we may have wanted to give the remaining half of the 20 megahertz channel, for example, to station 1 to reduce the transmission time. Okay, but we were only able to allocate, as I said, one resource unit to each station. So as we just saw in the previous example, a key limitation of OFDMA in 11AX is that we may end up not using all the channels. And why is that? Again, because 11AX can only assign a single resource unit to each station. So such restriction may lead to a waste of resources, especially in scenarios with a small number of stations. So if multiple resource units can be allocated to the same station, the station could use them to send the same data over several resource units, so improving the chances of correct reception through diversity, or it may simply send more data, so increasing the throughput, okay? So you see the example at the bottom of this slide. If you assume that the access point has data only for one station, then the access point can assign only the primary 20 megahertz channel to that station, but not the additional 40 megahertz, even if the preamble is punctured, okay? So a transmission towards this same station is not possible in the two red channels, okay? Which means the access point is using 20 megahertz instead of 60 available, okay? So 20 instead of 60 is a big loss. And why is that? Again, because only one resource unit per station can be assigned in 11AX. So to overcome this limitation, 11BE will support assignment of multiple resource units per station. So let's see how this brings gains in two different examples. The first example at the top, as before, we assume that there is only one station to be served, and the secondary 20 megahertz channel is busy. So in this case, we do preamble puncturing, and it allows us to assign 60 megahertz to this station. So remember, in the previous example with 11AX, only 20 megahertz could be exploited. Now 60. In the second example, now we assume that there are two stations, okay? There are 80 megahertz available, and in this case, station 2 only needs 20 megahertz, okay? It doesn't have a lot of traffic, but station 1 would want as much as possible, okay? So if you recall, with 11AX, it was not possible to assign the red 20 megahertz channel because only one resource unit could be given to station 1, but in 11B this will be possible. So in 11B, the access point can allocate two resource units to station 1, one of 40 megahertz and the other one of 20 megahertz, so it makes full use of the bandwidth. So besides frequency and time, one can also leverage the spatial dimension to achieve substantial peak throughput enhancement. So this is the reason why 11B will be increasing the maximum number of spatial streams from 8 to 16. This change would be particularly useful for indoor operations, which have a rich scattering environment and high angular spreads. So this allows to more easily separate information in the spatial domain, okay? So to better understand this, let's introduce the concepts of MIMO and spatial multiplexing. More antennas and better spatial multiplexing capabilities have been consistently added to Wi-Fi access points over the years. If you recall, we saw this when overviewing the history of Wi-Fi's evolution, right? So what can an access point do when availing of multiple antennas? So if the station also has multiple antennas, then the access point can transmit multiple streams simultaneously through what's called a single user MIMO, okay? And the maximum number of streams is capped by the minimum between the number of antennas at the access point and the number of antennas at the station. So for example, if the access point has 4 and the station has 2, a maximum of 2 streams can be transmitted to the station, okay? So alternatively, the access point can send one single stream to the station, as you see at the bottom of the slide, but focusing its transmission towards the station with what's called beamforming, okay? It should be noted that regulations in the unlicensed band don't allow to focus energy towards a particular direction, so when using beamforming, the access point should correspondingly reduce the transmit power rather than operating at maximum power. But beamforming can be very useful in reception too. So what we saw in the previous slide refers to using multiple antennas for communicating between an access point and one single station. So a yet more powerful technique is spatial multiplexing, where an access point can simultaneously transmit to multiple users at the same time and on the same frequency. This was introduced in 11AC, where access points were allowed to transmit up to 8 streams to up to 4 devices in downlink. So of course this had some limitations because many stations only had a single antenna, meaning that only one stream could be transmitted to such stations, okay? And second, in order to perform spatial multiplexing, the access point needs to estimate the channel between itself and the station very accurately. So this is typically done through channel sounding, where the access point transmits a pilot signal, the station estimates the channel and responds with the channel estimate. And these responses are serially transmitted, so the whole process can be slowed down. Finally, it should be also observed that having spatial multiplexing only in downlink means that the uplink becomes the bottleneck, for example, for the transmission of acknowledgements. So to address all these previous issues, 11AX already introduced spatial multiplexing in uplink 2, so enabled access points to spatially multiplex up to 8 single stream devices, both in downlink and in uplink. How does it work? Well, in uplink, as you can see in the figure, the access point will initiate a simultaneous transmission from each of the stations through a trigger frame. So when multiple users respond simultaneously with their own packets, the access point needs to separate them. So it applies some spatial matrix filter to the received beams and separates the information contained in each beam. Each multi-user MAMA transmission may have its own modulation and encoding scheme, a different number of spatial streams, and to coordinate these transmissions, the access point sends precisely the trigger frame to all users, and this trigger frame will indicate the number of spatial streams, DOF-DMA allocations, power control information such that each user or each station can increase or reduce the transmitted power according to the radio distance from the access point. Okay, the access point also needs to tell all users when to start and when to stop transmitting. So once the access point receives the frames from all users, then it will send a block acknowledgement to complete the operation. So accommodating up to 16 spatial stream instead of 8 could be doubling the spectral efficiency in 11BE compared to 11AX, right? So this seems very appealing too. But once again, one of the bottlenecks as we increase the number of antennas and the number of streams is channel state information acquisition. So the spatial multiplexing gains that we could achieve may actually be limited by the overhead that the channel sounding process entails. Okay, so this process is crucial to acquire channel state information precisely and therefore to place beams in transmission and also in reception. So if we double the number of spatial streams, but we still reuse the same explicit CSI acquisition procedure that is currently used in 11AX, well, this might not be scalable. So why? How does it work in 11AX? So if you look at the figure, well, 11AX employs what's called an explicit feedback procedure, which is similar to the one in 11AC. So the beamformer will send a null data packet, a null data packet announcement frame, then a null data packet, and which is basically a PPDU without data field. Then the beamformee, the station, for example, will measure the channel and will respond with a beamforming feedback frame. Okay, this contains some sort of a compressed feedback channel matrix. Okay, and then the beamformer, which is the access point, for example, will use this to calculate the channel matrix and will use it to focus the radio frequency energy towards the station. So can we do better? Well, there are two alternatives. One is to reduce the sounding overhead, basically the beamforming feedback frame, making it shorter, more compact. And another one is to do implicit CSI acquisition. So 11B is considering this implicit channel sounding procedure, which would rely on pilot signals transmitted by the station this time. So this would exploit channel reciprocity, because if a station sends a pilot, then the access point measures the channel in uplink from the station to the pilot, but because of channel reciprocity, this is the same as the channel in downlink. So besides increasing bandwidth up to 320 megahertz through channel bonding, and also increasing the number of spatial streams, as we've just seen, it's quite natural to increase the nominal data rate by increasing the order of modulation, in this case up to 4K QAM. So for high SNR scenarios, for example with short-range communications, which are quite typical sometimes in Wi-Fi, higher modulation encoding schemes can provide higher data rates, obviously. The thing to notice is that this goes logarithmically, so each additional increase in the order of the constellation gives a smaller and smaller gain, right? So when in 11AC 256 QAM was introduced, this gave a 33% gain compared to a 64 QAM. And then in 11AX, this was upgraded to 1024, and this gave a gain of about 25%. And if we had to go up to 4096 QAM, this would give just 20% gain. And at the same time, notice that the cost of such a small gain is pretty high, because you can see on the right of this figure how dense 4K QAM constellation is, and the SNR needed at a receiver to accept such constellation is about 40 dB, which is quite high for a typical Wi-Fi scenario. So in practice, such a high SNR can be achieved with beamforming. So for example, this 4K QAM modulation can be feasible when an access point has many antennas, but serves only one station which has few antennas. So in this case, multi-user transmission cannot be used because there is only one station and the station has few antennas, so it cannot receive many streams. So because the number of spatial streams is low, well, one could send one spatial stream, but with a very high order constellation. So now I'm going to start discussing other important 11BE features, and some of these might take just a little longer to be defined in the standard, as they're disruptive. They're not just incremental improvements over 11AX. So the next one I'll describe is HARQ, which stands for Hybrid Automatic Repeat Request. Current Wi-Fi systems rely on the retransmission of MEC protocol data units when these are not successfully decoded, or simply when an ACK is not received by the transmitter. So in this ARQ approach, automatic repeat request, the receiver discards the failed MAC PDUs before receiving its retransmitted version. So this does not allow for soft combining. And with the new reliability and latency requirements, it's arguable that 11B should evolve towards what's called hybrid ARQ capabilities, or HARQ. So with HARQ, devices attempting to decode a retransmitted MPDU do not ignore the previous unsuccessful MPDUs, but instead they combine their soft bits. So this way they increase the SNR and also the probability of decoding the packet correctly. So the HARQ mechanism is already implemented in cellular systems, and it can provide SNR gains of approximately 4 dBs compared to ARQ. This in an ideal AWGN channel. Of course, the throughput gains could be different when considering realistic Wi-Fi scenarios that have bursty interference due to collisions. Importantly, HARQ is also more robust to the errors in the estimation of the SNR at the receiver. So this allows the transmitter to select a higher modulation encoding scheme opportunistically. So either the transmission is fast with a good channel and a high MCS, or the receiver will extract some information anyway with a poor channel and will decode the packet through a retransmission, avoiding this way to reduce the MCS for such retries. The soft combining of HARQ requires some extra computational capabilities and also memory requirements, because we need to store past transmissions. So further studies are expected to evaluate performance and also complexity requirements. One of the expected revolutionary changes in 11be or Wi-Fi 7 is native support of multi-link operations, which is favorable for both high data rates and low latency. Let's see more about this. So you can think of multi-link as multi-band or multi-channel. So with the emergence of dual radio stations and tri-band access points that are capable of simultaneously operating at 2.4, 5, and soon 6 gigahertz, one of the main objectives of 11be is to make more efficient use of these multiple bands. In particular, notice that although modern chipsets can currently use links simultaneously, these links are actually independent, and this limits the efficiency of such operation. On the other hand, 11be strives to find such a level of synchronization between the links that would allow the most efficient use of the channel resources. So with three bands available, it makes sense to design systems that can exploit them simultaneously. So what can one do with them? One could do load balancing according to traffic needs. For example, this means assigning a station to different bands depending on the radio distance. Okay. Dual band access points can transmit simultaneously using 2.4 and 5 gigahertz, but to different stations because stations are generally single radio, so they can only operate on one frequency at a given time. One way forward from this is to let stations have simultaneous transmission and reception capabilities on different frequency bands, which is currently not possible. And this way they could aggregate data. Data transmission and reception separated in different bands can help to further reduce latency. So not only data traffic can be sent and received simultaneously, but also ACKs can be sent in a different band. Also, separating control and data plane could be useful. In fact, many transmissions require information such as buffer status in order to guarantee efficient resource allocation. But currently, acquiring this information introduces overhead, so there's a delay between the acquisition of the information and the response to that. For example, because listen before talk has to be performed. Another example is to transmit the nav, network allocation vector status, in a high band through a lower band and react accordingly. So this slide shows an example of multi-link operations across two bands, 5 GHz and 6 GHz. We have listed several ways to exploit the availability of the two different bands, and in this slide we'll see, for example, opportunistic link selection, link aggregation, and full duplex. So we see packets arriving in downlink or in uplink on the slide with their respective numbering. We see channels marked as busy in gray, used in downlink in yellow, and used in uplink in blue. Right. So for the first packet, if we look at the slide, which is to be transmitted in downlink, you see the D with number 1. The 6 GHz channel is opportunistically selected because the 5 GHz channel is busy in gray. Okay. Then for the second packet, both links are available and both are used simultaneously through link aggregation. So the downlink transmission of this packet is quite fast. Then the 5 GHz band is used for the first uplink packet, right, in blue, because the 6 GHz band is busy when that packet arrives in the queue. And the same thing occurs for the third downlink packet in yellow, which is transmitted on the 5 GHz link. Then when the second uplink packet arrives in the queue, full duplex transmission is exploited, and this packet is transmitted in uplink on the 6 GHz band, while the previous downlink packet is still being received on the 5 GHz band. Great, so now let's focus on another disruptive framework introduced in 11be, which is multi-access point coordination. We'll see how it can be applied to enhance spatial reuse. First of all, we'll look at two lower complexity implementations, which are called coordinated spatial reuse and coordinated OFDMA. So the idea of spatial reuse was one of the main innovations in 11ax already, and the idea is very simple actually. So even if there is an ongoing transmission, maybe another device can also start a new transmission without interfering to the ongoing one, and this will increase the network performance. The approaches introduced in 11ax are, however, uncoordinated, as opposed to the coordination to different extents, as we'll shortly see, introduced in 11be. So, for example, in OBSSPD, which stands for Overlapping Basic Service Set Preamble Detection, which is illustrated on the left of this slide, the main idea is that the transmission power is a function of the received power. So, for instance, as you can see in the figure, to be allowed to start a transmission with a power of 21 dBm means that the received power must be lower than minus 82 dBm. So if a device wants to start a transmission but the received power is higher than minus 82, it can still do it, but it needs to reduce the transmission power accordingly. Cool. Another mechanism, which is introduced in 11ax, is parameterized spatial reuse, or PSR, which is illustrated on the right of this slide. So with PSR, when an access point initiates uplink transmissions by using a trigger frame, it can activate spatial reuse opportunities. So other devices, different than the targeted one, receive and decode the trigger frame, and they use it to identify the spatial reuse opportunity along with the transmit power constraints and the maximum transmit duration. So we'll get back to PSR and how 11be could build on this framework to implement advanced AP coordination. So AP coordination is exactly what its name says. It means that multiple nearby access points decide to coordinate the transmissions. So this is a new disruptive feature in 11be. The goal is the one of removing contention between basic service sets to improve the throughput and, of course, to reduce latency as well. What does it require? Well, it requires over-the-air coordination, which might introduce some overhead. Also, new frames must be defined, including new multi-access point trigger to initiate coordinated transmissions, and also new mechanisms and protocols to create and manage the access points that belong to a certain coordination group. So in the example at the bottom of the slide, you can see how access point 1, as the master, sends a multi-access point trigger to initiate the multi-access point transmission. Okay, so let's assume that the multi-AP trigger indicates that the channel of 80 MHz, for example, which is shared between the two access points, is equally split between AP1 and AP2. So each of them takes 40 MHz, and after this initial phase, they can simply start the transmissions independently. But they use the agreed split of the spectrum such that no channel contention is necessary. So in the example, AP1 starts a downlink transmission in light blue, and AP2 starts an uplink OFDMA transmission, which is the two transmissions in yellow. And then in the following, we'll overview two low complexity access point coordination solutions that follow this kind of framework. One is coordinated OFDMA, which works in the time and frequency domain, and another one is coordinated spatial reuse, which works in the power domain instead. So let's start with coordinated OFDMA. The previous example is nothing but a case of coordinated OFDMA after all. So as you can see, this is a relatively simple technique for multi-access point coordination, because with coordinated OFDMA, the access points can jointly allocate time frequency resources, and this is attractive to minimize latency because it reduces the contention time. So now traditionally, the problem to solve when deploying a new Wi-Fi network is finding an idle chunk of spectrum. But now the question is, with coordinated OFDMA, should this approach be revisited? Because in order to benefit from cooperation between multiple access points, part of the spectrum must actually be shared and overlap across basic service sets. Another relatively simple technique for multi-AP coordination in 11be is called coordinated spatial reuse. It's a power domain technique. This will be an evolution of the spatial reuse mechanism introduced by 11ax. So spatial reuse in general is useful when the inter-BSS interference is weak, but the channel state is perceived as busy, so any other possible transmission is put on halt. Okay, so as we saw in 11ax, we have uncoordinated spatial reuse, where one access point transmits with maximum power, and the other access point should decrease its power to transmit concurrently. In 11b, this is extended by enabling access points to cooperatively control the transmit power, for instance, to maximize the aggregate throughput. So in the figure on the left, access point 2 is trying to use the spatial reuse opportunity, but its transmission is going to fail because the amount of interference at the destination, which is station 2 in green, is higher than expected because station 2 receives interference from access point 1. Okay. In the figure on the right side, instead, with coordinated spatial reuse, access point 1 and 2 have agreed on the power levels to be used, so both transmissions succeed now. So access point 1 is reducing its power level, which is still high enough to deliver the packet to station 1 in light blue, but now the interference on station 2 in green is low, so the packet sent by access point 2 to station 2 can also be delivered successfully. So we saw that 11BE plans to take access point coordination and spatial reuse to the next level. Now I'm going to describe two more sophisticated approaches for AP coordination, which may be somewhat more complicated to implement and might take a longer time to standardize compared to the last ones, but they also promise higher gains. So these two approaches are coordinated beamforming and joint transmission. Let's see more about them. So the approach to the left on this slide is distributed MIMO or DMIMO, also called joint transmission. So DMIMO is the most sophisticated solution in terms of coordination complexity that is being considered by 11BE. In DMIMO, non-collocated access points perform joint data transmission or joint data reception to and from multiple stations, right? So compared to systems with independent access point, the tight inter-access point collaboration of the MIMO can provide extended coverage thanks to additional beamforming gains, and also because the neighboring access points now are turned from interferers to servers. So achieving these gains requires inter-AP collaboration because you need to jointly process the data and the CSI of all stations, and this needs a high capacity, low latency backhaul, for example, fiber or millimeter wave. And importantly, the implementation of DMIMO in 11B would require designing new distributed CSMA-CA mechanisms to optimize channel access, also to guarantee fair coexistence with other independent access points that are deployed in the same coverage area. Another challenge is the tight synchronization required in time, frequency, and phase. So for this reason, it has been proposed to implement DMIMO with like master access point that oversees the cluster operation. This might limit the performance gains, but it could greatly simplify the coordination requirements. So just to clarify, the idea here would be for a master access point to send a trigger frame to the participating access points, and this way pre-compensating for phase drifts and frequency offset before the DMIMO transmission. So the second approach I'm going to mention here, which is illustrated to the right, is called coordinated beamforming, or also coordinated null steering. So what is this about? So multi-antenna access points typically use their capabilities for spatial multiplexing stations, right, in the same time and frequency resources. Also to provide useful signal power gains through beamforming. But alternatively, access points can also leverage their antennas to place some spatial radiation nulls to and from non-associated stations in the neighborhood. So this is shown in the figure where you see the access point 1 is suppressing the interference generated to station 2 with a radiation null. You see this in a red dash arrow. The same thing is being done by access point 2. Access point 2 suppresses interference to and from station 1. So this approach would boost spatial reuse by enabling simultaneous data transmission of devices that are within the same coverage area. So when you compare this to coordinated OFDMA, coordinated beamforming requires a further degree of cooperation, of course, because you need to organize scheduling decisions. You need to facilitate the acquisition of channel state information from these non-associated devices, because this channel state information is essential if you want to place radiation nulls properly, if you want to suppress interference properly. So coordinated beamforming has been included as one of the features in the specification framework document. It's really promising in terms of the gains that it can provide with a limited complexity. We can see it as a trade-off between simple access point coordination and very complex access point coordination, as in joint transmission or DMIMO. So in what follows, I'll show you how coordinated beamforming can really help achieve low latency communications. So in this final part of the webinar, I'll show you a detailed performance evaluation for coordinated beamforming conducted by my colleagues at Nokia Bell Labs. So we'll compare this feature to state-of-the-art 11AX approaches to evaluate its effectiveness. So let's consider three scenarios. So first, we consider a baseline 11AX system without any PSR capabilities, where the spectrum is shared with classical CSM ACA rules. So as shown in the figure at the bottom, this entails that devices may listen to each other, and therefore they have to alternate their transmissions. The second scenario considered is an 11AX system with PSR capabilities, where access points may grant some spatial reuse opportunities to stations in other basic service sets when they trigger uplink transmissions. So as you can see in the figure here, this can provide spatial reuse opportunities to those devices that are able to comply with certain interference thresholds set by access point 1, who is the one granting the spatial reuse opportunity. In particular, in this figure, the two stations that are located the furthest away on the right find the spatial reuse opportunity, and the one at the top right is actually performing a transmission with a constrained power towards access point 2. And the third scenario considered is an implementation of coordinated beamforming, where now the access point that triggers uplink transmissions can also grant spatial reuse opportunities to devices in another basic service set that have placed radiation nulls. Okay, so from the figure, you can observe how access point 1 now steers radiation nulls towards the two closest stations that are associated to access point 2. Right, so the two on the left. This allows these stations to find more spatial reuse opportunities, and which was not possible with a power-based scheme of 11AX. So what's the main advantage in this case? Well, it's that the green station at the bottom left of the green basic service set now is able to transmit towards access point 2 thanks to the radiation null placed by access point 1. So before showing you the results, let me provide further details regarding the simulation scenario. So there are two types of traffic considered: uplink broadband traffic, which is modeled as a file transfer protocol service, and uplink low latency traffic, which is modeled as augmented reality. Right, so the details are given on the right. So when triggering uplink, the access points will spatially multiplex as many stations as possible of the same class of traffic for each transmission opportunity. And the remaining spatial degrees of freedom will be leveraged to suppress interference from stations that have low latency traffic. So that's why access points will suppress interference only from the neighboring stations that have the strongest average perceived interference and that are generating low latency traffic. This will help those stations to find more spatial reuse opportunities and therefore to transmit more often, reducing their latency. We'll see that. So here's the detailed simulation setup. In particular, notice that we consider 2 access points and 24 stations uniformly distributed. And the scenario is quite dense. And out of those 24 stations, 16 generate broadband traffic and 8 generate low latency traffic. The access points have 8 antennas, and we limit the maximum number of radiation nulls to 4. So now we're ready to move on to the simulation results. So on the right, I'm showing you the delay performance achieved in the three scenarios. So in particular, you see the median, the 5%, 1%, and 0.01 worst MAC layer latencies experienced by the low latency stations, right? So we see that 11AX devices, so the blue and red bars, so with or without PSR capabilities, do struggle to maintain consistent low latencies in the worst cases because we're considering a dense and loaded setup in this experiment. So indeed, the latency remains around 3 milliseconds in 50% of the cases, but it can even exceed 200 milliseconds in the worst cases, right? So instead, 11BE with coordinated beamforming, which is represented in oranges or orange or yellow, allows for a 9.5 times reduction of the worst case latencies, which is almost one order of magnitude if you see. This is obtained by having a more aggressive spectrum access thanks to the strong inter-BSS interference mitigation produced by the nulls, okay? And while it's not shown in the figure, 11BE with coordinated beamforming is also able to roughly preserve the throughput of the other devices, the ones requesting broadband traffic. So in that case, there's just a slight reduction caused by the fact that the received beamforming gain is smaller because some degrees of freedom are allocated to suppress interference rather than for beamforming gain. But this reduction is really minor. It's been a pleasure to give you an overview of 802.11be. By now, I bet you're able to answer the question, what is Wi-Fi going to be like in 2025? So for more details, I've listed a few references related to the topics covered today. In particular, I recommend our magazine paper, reference number 1, which is the one that best summarizes the content of this webinar and which has also received international press coverage in something like 7 or 8 languages. So do subscribe to this channel if you want to know when I upload something new, and see you in the next video.